our recent effort in studying the dynamics of the AI development competitions and how to regulate that competitions for societal benefit. So this is joint work with Tom Lenaerts, Luis Moniz Pereira, and Francisco Santos. Okay, so recently there's great expectations about the benefit and the potentials of AI that can bring to many domains beyond technological sector. So there's great expectations about that AI can change the world, can bring lots of step change to businesses. And because of these expectations of the potentials of AI technologies that it might bring to business and to countries, there's a certain concern about there could be an embrace about within AI technology development among different countries, companies, because there's great benefit to be the first to reach supremacy in certain technologies. So, because of this concern about a potential race among different development teams, which might lead to very severe consequences, because to be the first, teams might choose to cut corners on safety compliance. And they may, okay, we just want to be the first to reach a certain target, so probably just ignore all the safety compliances so that we will be the first to reap all the big benefit, all the great benefit that certain technologies, supremacy might bring us. So because of that, there's lots of effort in developing kind of regulations framework to ensure that AI technologies are developed in a safe, ethical, and responsible way. For example, the recent white paper from EU emphasized the need for a regulatory framework which is based on risks of certain technologies. So in order to think about how we can regulate these technologies, race, or development competitions in a suitable way, there's a number of questions we need to think about, we need to answer. For example, what do we actually know about the dynamics of this alleged AI race? We say alleged because we don't know exactly to what level the competitions is a race. And if we understand the dynamics, then we can ask the questions, what do we know the impact of certain regulatory actions on such race dynamics? If we implement certain regulatory actions, what is the impact, what is the effect? So we need to understand that. And we also can think, oh, whether regulation is actually any useful and useful in what sense, because we know that if we over-regulate certain technologies, for example, something that is not that risky, and the government put a lot of regulations on that technologies, that might stiffen the innovations. So these are some of the questions that need to be answered in order to devise suitable regulatory frameworks for AI race regulations. In our recent work, we have made an initial effort to answer the first questions, where we used methods from evolutionary game theory and agent-based simulation to provide for the first time a model to describe the competitions between different actors within an AI development race. So we study the tensions between safety compliance and innovations, meaning risk-taking behavior. So I'm going to talk briefly about that, but you can look at the paper for more details. After that, I will show you some of our effort to answer the questions 2 and 3, where given a baseline model describing the AI race, we study different kind of regulatory actions to influence the AI race dynamics. Okay, so let's say we have an AI supremacy in a certain domain, for example, speech recognitions, robotics, driverless car, and there are a number of development teams are racing, trying to reach the AI supremacy in that domain. And to reach the supremacy, we assume that there are W advancements that need to be made. In each the advancement, the development teams can reap some benefit from deploying their intermediate product. So we have studied like multiple race among multiple teams, but in this paper, in this talk, I'm going to focus on 2-player race. So in each advancement, there's choice to be made from the team. So they can choose to play safe, meaning comply with the safety precautions, or they choose to ignore the safety precautions by playing unsafe. And clearly, safe is more costly and takes more time than playing unsafe. So here we assume that the speed for playing safe is normalized to 1, while the speed of unsafe is something greater than 1. And from that, for using evolutionary game theory, we need to derive the payoff. For example, here in a 2-player or 2-team racing, if you have, say, a safe versus a safe, then each safe player need to pay a cost while share the benefit, the intermediate benefit from a round. While if safe plays against an unsafe, it still pay a cost, but get a less benefit, while the unsafe reap a large part of the benefit without having to pay a cost. So we also need to define what are the possible strategies in this race. In our analysis, we consider the player who always play safe, denoted by AS, so always comply with safety compliance in all routes of development, or you have AU who always play unsafe, always ignore safety precautions, or you also can have those who use combinations of safe and unsafe from different routes. And when there's unsafe actions involved, there's a risk of disaster. So saying, okay, if all the teams ignore safety precautions, there's a risk that you get some very unsafe technologies, maybe can destroy the world, and everybody lose everything. And we can define the risks in this way. So assume that P risk is the probability that when if safety precaution is completely ignored, then with the probability P risk that a disaster will occurs. And then the rest is proportional to this, depending on how many unsafe actions is done. And now we can derive what is the average gains for each player, each type of player. Here you can see that AU even can win the race, but there's a probability that it will lose everything because of certain safety, unsafe behavior was involved. To analyze this, we use a technique from evolutionary game theory. Here is we use social learning process. I'm not going to talk in detail about this, so you can look at the paper. Here is a standard process for implementing social learning via either mutations or explorations. Okay, so now we can ask the questions, okay, what behavior dominates? So here we consider populations of 2 types, always unsafe or always safe. So we can ask, okay, what behavior dominates and which parameters influence dominance? And we also can answer questions like what regulatory actions are required and when they are not required. So here we plot the unsafe frequency as a function of the development speed given a risk probability. We can derive analytical conditions when, so this white line here indicate that above that line, then safety behavior would be more beneficial than unsafe behavior. So if you have a population of safe, it is more beneficial for the society. But because through social learning, we also can indicate conditions where, so even you preferred safe, you actually cannot get that. So that these two lines give us three zones. So we say this is the innovation zone, which is where you want innovations, risk-taking behavior, and actually you get it through natural selections or social learning. And you have the compliance zone here, where you want unsafe, you want safety compliance, and you actually get it. But there's one area, one regions where you want safety compliance, but you cannot get it because natural selections would lead to AU to dominate the population. So clearly here we can say, okay, in compliance and in the innovation zones, nothing needs to be done because whatever we want, we already get it. And in the dilemma zone is where regulatory actions are required. So, so here in our work we studied. Okay, we study different form of incentives. Yeah. So here we have this punishment that can reduce unsafe opponents. Yeah. So here, for example, if you see that somebody doing something unsafe, you can punish and which reduce the speed of that unsafe players. Similarly, we also can do reward where you can actually, like somebody doing safe, you can reward that by, for example, sharing knowledge and help promote the speed of the co-player. So here the final result. Yeah. So here we look at the effect of these negative and positive incentives on safety compliance, and we see that in the dilemma zone, both these type of incentives can actually reduce the unsafe behavior which is desired. Why in the compliance zone nothing happens, because actually we just promote the safety behavior and we already have that. But the worst scenario which need to be resolved in future work is that punishment might lead to over-regulations. If you have very strong punishment of safe behavior, why you actually want innovations is actually lead to over-regulations. So, okay, so you can read more from our paper. So to summarize, I have described here a plausible model that can be useful for thinking about policy and regulations in AI development race. And we have shown that both punishment and reward can improve safety compliance in the dilemma zones, but punishment might lead to some kind of undesired behavior, which is over-regulation of innovations, where innovation is preferred. Yeah, so it's just a proof that, okay, we can use game theory, evolutionary game theory, to understand this very complex process, and this is our initial effort. Okay, okay. You can check. Yeah. Okay, it's just okay. We thank sponsor from Future of Life Institute.
Okay, thank you very much, Tian. Are there any questions? We have little time for round of the questions.
Yes, can I ask one quick question?
Yes, of course.
Yeah. Thank you, Tian. It's very interesting work. So can you generalize this kind of model to the more continuous scale of the whether it's safe or unsafe? I'm asking this because in reality, like a COVID vaccine, the development, the people take more risks to expedite the process. So what happens if the scale becomes more continuous.
Yeah, it's definitely, that's one of our future work. So here we just say, okay, whether you can either play safe or unsafe, but you also can say, okay, the action is to what level of safety precautions you should take, and it depends on certain technologies. I guess great questions. Thank you. Yeah, that is in our plan to explore.
Thank you.
Okay, is there any other question?
I have another question. If there's
okay, yes, I think for this question, yes.
Okay. Hi, Dan. It was a very nice presentation. Let me know if I understood it correctly, but if I understand correctly, the risk that you're modeling is a personal risk. It models if a player may lose their endowment, but it's only personal, right?
Yeah.
What would happen if there was some kind of collective risk?
Yeah, so it did. Yeah, so I think I wrote there, but I didn't say we consider both cases. Yeah, so where the risk might be personalized or it might be shared by players involved, as in case of climate change. I guess you to talk about collective risk, but in the we show that collective risks lead to very similar results, at least in this scenario. There's scenarios where there's different effects, but yeah.
Yeah, that's very interesting.
Okay, thank you very much for the presentation, Tian, and for the questions. We're going to pass to our next speaker, which is Elias Fernández, which is going to present Time in Uncertainty encourages group reciprocation and polarization in collective risk dilemmas. The floor is yours.
Okay, so I made a video. I'm gonna attempt to share it.
Okay.
I hope it works. Let me know if you can hear it. Can you see it in the image?
Yes, I can see it. Yes.
Okay, I'll start it. Let me know if the voice works.
Okay. I don't listen to something. You must share your. I think there is a place where you must share your sound.
Sorry.
There is an option to share the sound. I think.
Do you know where this option is?
That's a good question.
First, you need to stop the screen sharing and then the reshare. And when you click the share screen button, there should be a tiny checkbox.
Okay, thank you.
Share computer audio or something like that.
Thank you, Hiroki.
No problem.
The option is on the bottom left.
Yeah, I think I found it. Just a second. Can you see my screen?
Yes, I can see.
Hello, thank you for attending this talk. My name is Elias Fernández, and in this presentation, I'm going to talk about the results of a behavioral economic experiment that we performed in the context of the collective risk dilemma. In this dilemma, the returns that participants may obtain are not only uncertain, but also delayed in time. But before I introduce the collective risk dilemma, let me explain what I mean by collective risk. And let's do that by taking climate action as an example. Obviously, this is a very complex problem. But if we look at it from a socioeconomical perspective, we have several countries with different ideologies, political systems, and economic perspectives, and they all have to cooperate in order to avoid the consequences of a future climate disaster. However, the measures that need to be taken may have an initial negative impact on the economy of heavily industrialized countries. So some of them may feel the temptation to defect and hope that the effort that others will put will be enough. But if this reasoning is extended to every other country, we may end up in the well-known tragedy of the commons, and climate catastrophes will very likely happen, impacting everyone. This is what we call collective risk. And it's present in a number of other collective endeavors, such as group hunting, vaccine hesitancy, or antibiotic abuse. Of course, again, these problems are all very complex. So in order to isolate the factors that we want to study, we'll abstract them into the collective risk dilemma. And in this dilemma, we give an initial equal endowment to a group of participants, and we ask them to make discrete contributions to a public good throughout a certain number of rounds. after the last round, so at the end of the game, if the participants jointly contributed above a certain collective target, above or equal a certain collective target, then they may keep whatever remains from their personal endowment. However, you see that even the situation may not be fair, and participants may have put different amount of efforts. In contrast, if the group does not reach this collective target, then there is a risk or a probability that they will all lose their remaining endowment, meaning that they will end up with a payoff of 0. So this dilemma may have many sources of uncertainty, which can have a big impact both on the outcome as well as the behavior of the participants. One of them is the risk that we just mentioned, but the collective target may also be uncertain, or the number of rounds that is available to reach this collective target may be unknown. And this last type of uncertainty is the one that we are going to study or present in this talk. So to model this type of uncertainty, which we call timing uncertainty, we draw the total number of rounds from a stochastic geometric distribution, meaning that after a minimum number of rounds, there is a probability 1 minus W that the game will end. And otherwise the game will continue, and after the next round, another dice will be thrown until the game ends. And this W represents our timing uncertainty. So we performed a controlled experiment in a laboratory such as the one you see in the picture, in which we had 246 human participants. Each participant started with an endowment of 40 units, and each group had 6 players which had to achieve a collective target of 120 units. And we only consider a high-risk situation, so risk is 90%. And we had 3 treatments, and all treatments had on average 10 rounds. And at each round, participants could contribute 0, 2, or 4 units out of their endowment. In our first treatment, which we call no uncertainty, participants knew exactly that they had 10 rounds to achieve the target. In the second treatment, which we call low uncertainty, there was a minimum of 8 rounds, and afterwards the game would continue with a probability of 2/3. Again, on average, the game had 10 rounds. Finally, in the third treatment, which we call high uncertainty, the probability that the game continues after the minimum number of rounds is higher, which increases the uncertainty about the game, about when the game would end. But again, the average number of rounds is 10, and participants knew this. In our experiment, participants interacted through a web experimental platform, and this is what they could see in their screen. They could observe how much they contributed in the previous round and how much the other members of the group contributed in the previous rounds. These numbers always appeared in the same order so that participants could form a history of actions. However, all participants were anonymous, meaning that groups were formed randomly and participants could not identify who were in their group. Also, participants could observe how much was left of their personal endowment in their personal account. So firstly, let's look at how groups contributed through time and the fraction of successful groups. So in the figure on the left, we show the average group contributions during the no uncertainty treatment. And what we see is that the groups contributed pretty much a very similar amount throughout the rounds. In fact, they contributed only as much as was necessary to achieve the target only by the last round and not earlier. And there were 67% of successful groups. In the low uncertainty treatment, we see in contrast that there is an increase of earlier contributions. So more participants contributing more at the early stages of the game, while there's not a significant decrease in the group success, in the fraction of successful participants. However, this trend does not continue in the high uncertainty treatment. And actually, we see a decrease of group success. There is only 47% of groups that were successful. So to better understand what is really happening, we're going to group players based on their contributory behavior. But before, let me introduce a notion of fairness in this game. Here, if all participants contribute exactly half of their endowment, then the group reaches exactly the target and all participants will end up with the same payoff. We call this a global fair result, where the burden of the dilemma is shared equally amongst participants, and we represent this by the letter F. So here we show the fraction of participants in each treatment that contributes less than the sphere amount, equal to the sphere amount, or more to the sphere of the fair amount. And we see that in this first treatment, in the no uncertain treatment, most participants adopt the fair behavior. They contribute exactly the fair amount. However, with time and uncertainty, we see a decrease of this number of fair participants and an increase of participants that are having extreme contributions, contributing either more or less than the fair amount. So we see an increase in the polarization of contributions. Now, if we look at how participants in successful groups react to the contributions of the group in the previous round, we can also see a behavioral shift. In this figure, we are plotting the average contributions of participants in function of the contributions of the other members of the group in the previous round. The fitted lines indicate the direction of the conditionality, meaning that if the slope is negative, participants are being compensatory, which is contributing more only when the others are contributing less. And this is the behavior that we are observing in the no uncertainty treatment. In the treatments with uncertainty, in contrast, the slope is positive, indicating that participants are acting reciprocally, so contributing more only when the other members of the group are also contributing more. This is already very interesting, but we are only averaging the behavior of all participants in the experiment. So in order to understand or to find out what is the behavior, the actual behavior composition of the population, we have clustered participants in the experimental population using a DB-SCANA algorithm, which finds 4 different clusters and some outliers. And firstly, if we look at this purple cluster, which seems to increases in size in the time and uncertainty treatments, we see that it represents participants that are adopting a strong reciprocal behavior. While if we look at the red cluster, for example, which decreases in the time and uncertainty experiments, we see that it represents participants that are being slightly compensatory. Also, the orange cluster decreases in the time and uncertainty treatments and represents participants that are being strongly compensatory. While the most common cluster is this green cluster, which represent the participants that most of the time on average contribute exactly to, and only react to extreme contributions from the group, which is when the group is contributing either very much or very little. So this already is very interesting. We're able to discern what is the behavior composition of the population, but they still don't know why we see this change with time and uncertainty. So for that, we have created a simple multi-agent model of social learning in which we consider 5 strategies. 3 unconditional ones, where we have players contributing only 0, only 2, or only 4 in each round, and 2 conditional ones where players are being compensatory or reciprocal. Again, remember, compensatory is contributing more when the others contribute less, and reciprocal, the opposite. And in this model, we have a population of individuals, of agents, that adapt by imitating the best performing individuals, or through mutation. And this defines some dynamics that are represented, for example, in the simplest, if we have only 3 strategies. And if we assume that mutations are very rare, we can simplify the system and only look at the edges and form this Markov chain that you see here, which represent the dominance relationship between homogeneous states, which are when the population all the members of the population adopt a single strategy. So in fact, we have represented dominance relationship between the strategies, where an outgoing arrow represents a strategy being dominated by another. So if we plot this Markov chains for the no uncertainty treatment and the high uncertainty treatment, what we see is that in the case of no uncertainty, always 2 is dominant. It's not invaded or dominated by any other strategy. While in the high uncertainty treatment, this is no longer the case, and a cyclic dynamics appear, some kind of chaotic dynamics. So what we see is that the game is changing. And in fact, the appearance of the cyclic dynamics makes the increase of the proportion of reciprocals in the population. And in fact, we see that our model reproduces some of the trends of our experiment. We see a decrease in group success with time and uncertainty, and an increase in the proportion of reciprocals, and an increase in polarization of contributions. So to summarize, we see that uncertainty plays a big role in human behavior in these collective risk scenarios, and that time and uncertainty leads to polarization of contributions, and that successful participants adopt reciprocal behaviors. So it may be that contributing early is necessary to promote collaboration among the peers, to signal the willingness to cooperate. And finally, it's interesting that we are able to reproduce our results with a simple evolutionary model. Finally, I want to mention that these are the other contributors to the paper: Francisco Santos, Jelena, Grujić, Georg Kirchsteiger, Juan Carlos Burguillo, and Tom Lenaerts. Thank you very much, and I'll be very happy to answer your questions. Thank you.
Elias, thank you for your interesting talk. Are there any questions to Elias? Hiroki?
Yeah, I see something in the chat.
Yes, I posted
okay.
that, what if the belief system is different among the participants within the population? So like half of them believes that there is the time, and the other half, is more on high uncertainty situation.
This is very interesting. In fact, there is something that we didn't model or study in this experiment. That is, what is the difference in perceptions and risk depending on this time uncertainty. So one of our hypotheses is that time and uncertainty changes the risk aversion in the population, or at least elicits or brings more attention to this aspect of human behavior. And what you're saying is interesting. It would be interesting to see if people have half of the participants are playing the game as if there were 10 rounds, and the other half as if there would be 5 or more rounds. There would be a difference, but I don't know what would happen.
Thank you. That's exactly what's happening in the United States.
Okay, thank you. Is there any other questions to Elias?
Okay, so I see also something in the chat.
Okay.
What do you think the role of punishment by other players would have in uncertain scenarios? So punishment is a mechanism that is very well studied and is useful in general for cooperation. In this case, I don't know what happened, and it's certainly a future line of research that we are looking at. What happens if we add institutions? Because in the end, if we go again to the example of the climate game, climate is played among institutions, and it would be interesting to see what happens if we have punishment, social punishment, institutionalized punishment, and yeah, it would be interesting to see if this helps coordination. Again, it's important to see that when we have high risk, as it is in this case, we have a coordination problem, but time and uncertainty changes the problem and makes it creates some kind of chaotic dynamics. It would be interesting to see if punishment can break out the cycle and go back to a coordination problem.
There is also a question by Tian. Did you fit data with models, perhaps by finding a suitable intensity of selection?
Yes. I didn't put I don't think I have the picture here, but indeed we had a 0.04 intensity of selection, and that was fitted from the data to find out what was the results that will reproduce the best our experimental results. Of course, we will never reproduce exactly the experimental results because we don't have enough data to have a complete model. But also we are using a very simplified model and only consider 5 strategies. But it's interesting to see what are the dynamics there.
Okay, so I think we are on time. Thank you all for the presentation. Very nice, interesting questions. And we're going to pass to our next speaker. Thank you, Elias.
Thank you very much.
Hiroki, do you want to ask something?
Yeah.
No, I was just clapping.
Okay. Sorry, I'm not so familiarized. Thank you very much.
Yeah, just want to mention that the paper is published in iScience if anyone wants to look at it.
Okay, thank you. We're going to pass to our next speaker, Theodor Cimpeanu, if I pronounce well, who is going to present the paper Promoting Fairness in the Spatial Ultimatum Game. Theodor, the step is yours. The floor is yours.
Okay, so can everyone hear me okay?
Yeah, that's fine, yes.
Right, so I'll just talk a bit about promoting fairness in the Spatial Ultimatum Game. So first of all, thank you to my collaborators, Cedric and Tean. Tean is here, Cedric no, but I think many of you might know him already. So feel free to stop me at any time during the presentation because I think we're quite a small room, so always welcome for questions. And let's make a start, if this works. Yeah, so let's imagine we have a population of agents, and then we want to invest some type of financial, or not necessarily financial, but we want to invest with some positive incentive in order to promote a desired type of behavior. And we're talking about an institution that's completely external from the population. So we don't actually include any type of self-organized institutions, just kind of an external agency that has nothing to do with the population, but wants a desirable outcome. And one such example is this. This is the bison population in my home country of Romania. And the WWF basically wanted to restore natural bison population after this had gone extinct in Romania. So they took some bison from Poland and then reintroduced them in the habitat of Romania. And then they basically did stuff like collective feeding and stuff like that, just to promote the natural development of these bison. And after some successful attempts over, I think, 10 or 15 years, they managed to reintroduce them back into Romania. But if we move away from this example and consider kind of a more asymmetric environment, we can talk about the Ultimatum game. And for those of you who are not familiar, the concept is quite simple. You have some sort of individual endowment, just like Elias was talking about earlier, but in this case, just a different type of game. And one of the participating players in this game has the role of proposer. So in this case, they can decide how much of their endowment they want to split with the other person. So this could be a high proportion of the endowment or something very small. And the other person can, of course, either accept or decline. And in this case, we have another person who really wants the high proposal. So he won't accept anything less. So if the first player proposes something small, then the second player can say no thanks. And at this point, the endowment is lost. So just like in the kind of collective action problem, no one gets anything. But what happens on the other hand, if the initial player decides to propose a fair offer, then the second player accepts, obviously, and they both split the endowment as the proposer initially proposed. And in experimental situations, this could be something like a wide variety of options, right? You could split it 70%, 30%, or in any other proportion. But generally speaking, for kind of simulations, we decide on a fixed outcome with just a limited set of strategies. So what would we expect to happen out of this result? Well, obviously you would expect the proposer to propose low and the acceptor to accept anything. But that's not actually what happens, and experimentally it's not what happens. So lots and lots of people have come up with different explanations as to why this is. Just as is the case for the prisoner's dilemma, the Nash equilibrium isn't necessarily what happens in the real world. So one such real example of where you can apply the ultimatum game is actually any kind of negotiation. So in this case, either the Greek deal with the EU or Brexit, you have these large-scale negotiations where someone can propose something, and if they do not come to an agreement, basically no one gets to share that benefit. Right? So it's in the best interest of everyone to kind of come to a mutual agreement. And I'll talk a bit about the kind of the physical properties of the model. We have this payoff matrix if anyone is interested, and we fix high proposals to 0.5 and low proposals for 0.1 for simplicity. Although from our experiments, things are very, very similar if you just change things a bit. We have a spatial population, so in this case, a lattice. The reason we decided to include spatial populations is that we can actually think about more small scale incentive strategies where you look at neighborhoods and at individual kind of clusters. But at the same time, you don't have the huge complexity of more heterogeneous networks like social networks where you have to think about all the stochasticity involved, and it becomes a bit more complicated to understand the dynamics. And we use the Fermi function for social dynamics. So this is imitation. And we also have mutation, or in other words, social exploration, where players can randomly explore other kind of strategies. So we see there's basically, in the two roles, you can choose either high or low. So there's 4 possible strategies. These two at the beginning are the completely fair ones. So in most definitions, you would consider those to be fair, where you propose high and accept high, or you propose high and you accept anything. basically. And the other two are considered unfair, where you propose low and you accept anything, and you propose low and accept only high offers. So if you consider all of these strategies, you have some sort of role asymmetry. So when you decide to invest, and by investment, we just mean artificially increasing payoffs. So just increasing the payoff of the players that you want to invest in by an amount theta. And you can consider these three kind of situations where you would potentially want to invest. The first one was ensuring that all proposals are fair. So you invest only in A-change and HL. And in this case, you need the least amount of information gathering about the system. The second one would be to ensure that only fair offers are accepted. So obviously this is a bit more difficult to kind of gather. So this would be HH and LH. And then the final one would be to ensure that both fair proposal and fair offers are accepted. So in that case, that would be the most strict information gathering, and that's investing only in HH. And besides those kind of very simple investment targets, we also think about some investment strategies. So the first one would be just looking at the whole population and deciding to invest when the threshold of fair proposals is above a certain threshold that we want. So for example, we can say something like, or if we don't have enough fair individuals in the population, we can decide to invest in our targets. And similarly, we have neighborhood-based, in which case you look at specific neighborhoods, and exactly as we did in the population, if we don't have enough fair proposals in the neighborhood, then we can invest. And what ends up happening is actually very different from previous work done on kind of prisoner's dilemma and symmetric experiments. And we see that actually you don't need to worry too much about the individual investment. So in other words, investing even small amounts is quite successful because of the kind of inherent equilibrium between fair and unfair proposals on a lattice. And actually, in case of population composition based, it's very beneficial to invest in HH, obviously, where you have the strict information gathering, but it's not that bad to invest in the others. So in the case of prisoner's dilemma, for example, you have to be more strict, and you have to always kind of look at the threshold between what your investment cost is and what the threshold in the population is. But here it's a bit more simple. So in other words, as long as you're doing the work of gathering information, it's simpler to invest. And over here on the right, we see kind of the Pareto front. So we would expect the most efficient strategies to be on the bottom left of each plot. And in this case, we see that, first of all, investment size or individual endowment, doesn't matter that much. And that in the case of HH, it's simpler. So we see this curve going kind of closer to the bottom left, whereas in the case of the least amount of information gathering, HH and HL, we see the opposite happening, right? So it's a bit more complex. And if we plot the strictest or the most optimal outcomes in every situation for all different types of mutation rate, we basically get target HH in any case. So in other words, investing in HH is always the best. So it's always in the best interest of the investor to ensure that both fair offers and fair acceptance is promoted. And then in the case of neighborhood-based, we see kind of a very different trend where the investment strategy doesn't matter that much, but in terms of cost, it's always more efficient to go for a lower threshold. So in other words, if you have at least one fair, at most one fair individual in the neighborhood, you should stop investing. So if you have two or more, you should never invest. And you can see that in the Pareto front, it's always a threshold going closer to the bottom left is always that one. And then I'm going to discuss, and also in the different mutation rates, you have this kind of equilibrium between different targets, right? So you see both HH, HH, HL, and that finally some cases in which HH and LH are there. And that's basically just due to the stochastic nature of the system. These are all very close. So this just goes to show you how equal the different targeting schemes are in the case of local information gathering. And then just very briefly talk about mutation. So this actually is one of the key kind of advancements to the state of the art of our paper, is that previously people did not really consider mutation, usually just small mutation limit. So we see the effects of mutation and kind of how different interference strategies respond to mutation. And what we see in almost every scenario, and these are the optimal cases, is the fact that when you have more mutation, obviously you need to keep reinvesting in order to prevent any kind of staying away from the equilibrium, right? So whenever the population goes beyond below a certain threshold, you need to start investing again. And in different types of strategies, so for example, in the population-based, then you need to invest way more. Whereas in the neighborhood one, you have a bit more freedom where you don't need to reinvest as often. So the key findings very briefly are that it's very crucial to consider roles asymmetry in order to provide cost-efficient investment strategies, especially in the case of population-based. And this is completely different from other works done on lattice, such as Prisoner's Dilemma. Population-based approaches are characterized by the need of extensive information gathering. So the more you stay away from kind of local observations, the more you need to gather information about other things. And then neighborhood-based approaches, so the local information gathering, they're more flexible. You don't need to worry that much about strategies, but you can maximize the solution. So you can always provide the best outcome and the least amount of cost if you don't overinvest. So you only need to ensure that there is at most one player with a desirable behavior, and then you can stop investing and everything is fine. So yeah, I think that's it. How are we doing for time? That's basically it.
Yes.
I'm welcome to any questions.
Okay, thank you, Theodor, for your interesting talk. Are there any questions? We have time for questions, I think. I will ask a question. Did you try, Theodor, to apply this with real data or in real situation?
No, not yet, but yeah, it's definitely something we want to do, to calibrate the model with real data. But at the moment, it was almost an exploratory type situation where we want to understand the basic mathematical dynamics in order to gain any kind of interesting insight. Yeah. But thank you for the question.
Okay, so if there is another question, thanks again, Theodor. And we pass to the next speaker, which is Saint Luce, if I pronounced well, which is going to present a network-based phase space analysis of the El Farol bar problem.
Yes. Can you hear me?
Yes, yes.
Okay, great. Let me see. I have a video, so let me see if I can share my screen.
Okay. Okay.
Okay. Is my video visible?
Yes, yes.
Okay. Let's see if we can. Hey everyone, my name is Shane St. Luce.
Okay.
I am a PhD candidate at Binghamton University, studying systems science. I would like to thank the conference for inviting me to present my research that was conducted along with my advisor on a network-based approach for analyzing the phase space of the El Farol bar problem. So for those who are unfamiliar with the problem, let's say that there is a bar open once a week with capacity of about 60 people. And additionally, there are 100 actors who are all interested in going to this bar once a week, but have no way of communicating to each other whether or not they desire to go. And each actor is interested in going to the bar only if the bar will not be crowded. And if the bar is crowded, they would rather stay home. So the only information available to them is the previous attendance of the bar. And in this case, we find ourselves in a sense of bounded rationality. And so to help these actors make their decisions, they're given a set of attendance predictors, or what we can call strategies, each week. And over time, the idea is that they will learn which predictors are good and which predictors are bad, and to optimize their happiness. And so we came up with a few strategies, and considering a strategy as a predictor plus the action being taken. One is the last correct strategy. Simply the actor chooses the decision that was correct the previous week. The last incorrect strategy, which the actor chooses the opposite. The never strategy, actor decides never go to the bar. Always strategy, always goes to the bar. And then the last two strategies bend the rules a little bit. The random strategy is actor decides to go to the bar randomly with 60% probability in accordance to the capacity of the bar in relation to the population size. And the enthusiastic strategy, which is essentially if the actor has made more correct decisions in recent weeks than wrong decisions or incorrect decisions, then they will decide to go to the bar. This strategy is added here in particular just to see if this kind of analysis can even work beyond the original structure of the problem. So from the actor perspective, although there's clearly other actors in the system, since that's what the attendance is based off of, each actor can only see the bar and the previous attendance history when they're making their decision. They have their own bag of tricks, their bag of decision strategies, and they have to figure out which one to use from there. The system as a whole has a series, 100 of these actors, each with their own bag of tricks, each trying to pull out a strategy to use to decide on whether or not to go to the bar. And so now we have one possible outcome for, say, actor number one's perspective, where potentially a good amount of the other actors will decide to use the blue and black strategy, enough of which will lead them to go to the bar, making the bar crowded. And so in this case, this actor probably should use the red strategy, which would indicate not going to the bar, but they don't know that. That's why for the question mark. On the other hand, maybe most of the actors decide to stay home. Only a few people use the blue or black strategy to go to the bar. And in that case, that's the strategy that they would want to use. So this is actually a buildup of previous research that my advisor and I conducted, where we started off with running simulations of evenly distributed distributions for a set of strategies. And in the past, what we would use is last correct, never, and last incorrect strategies. And so from previous research, something that was really interesting here was that over time, the never strategy was just abandoned. But what we can see is that this kind of approach for visualizing this is spatially bounded. With three strategies, we need 2 dimensions. And so if we ever want to analyze the phase space with more strategies, we would need more dimensions. So this leads us to the idea of using networks. And so what we do here is that we notice that different distributions are have their own tendencies. And we can bottle each distribution up into a node and recognize that with the actor's ability to change their strategies over time, there may be tendencies for the distributions to change in certain directions. And so now we can see a few arrows pop up, and if we were to do this again, we could see that some transitions probably happen more often than others, and if there's a cycle, then we can indicate that there might be some potential for an attractor. So by taking this approach, we get some new results, especially visually. Using the same 3 strategies, last correct, never, and last incorrect, we get this network in a kind of circular layout where a lot of the nodes here have low in degree, meaning that there's not many distributions that are really leading into this kind of, into this other node. And then we have a select group of nodes with very high in degree, indicating that the many times these nodes are coming in, are being transitioned into. So after playing around with layouts, we try a force atlas layout, and we could actually see that the low end degrees on the right, the high end degrees on the left, the high end degree nodes, and we get a sense that the distributions, the strategy, the system state essentially is moving from right to left. And so after mulling on this for a little bit longer, we think about the concept of a strongly connected component, but really we're interested in a group of nodes that once a system enters that group of nodes, it has a tendency to stay in that set group, kind of like a sink. And so we add this concept of a sink strongly connected component to our analysis. And what we find is that, again, with the high-end degree nodes, they end up being part of a sink for the whole network. And if we were to expand on that, we trying other strategy sets, not only do we notice that there are sink strongly connected components and in the bottom three graph visualizations here, but we could also see that the topology is also pretty different, even though we're using the same layout algorithm. And so for this set of three strategy sets, we're using the random and enthusiastic strategies, the two that bend the rules a little bit, and we can still see that the approach still works fairly well. One interesting point is that the random enthusiastic last correct and random enthusiastic always strategy sets yield very large sink strongly connected components. However, we also can see from the in-degree networks that there's still kind of a central aspect to those components where the system still seems to tend to go to. So further, we analyzed the edge weights and noticed that there appeared to be a power law distribution in terms of how the system is moving, and which kind of makes sense because it looks kind of like streams approaching a lake. And if we were to do the same thing, analyzing the in degree and the out degree of the nodes, we again see a power law. So to test the theory about the dimensions issue, we actually tried this with 4 strategies, and here we can see that it actually still works. And this is with last correct, always, never, last incorrect strategies. So it's a strategy set of 4 total. And here, although each strategy follows in line with the original rules of the problem, we see that there's a seemingly very large sink strongly connected component, which we're kind of considering as the attractor in this network. And yet, again, we also see that there's a core on the left side that tends to have a higher end degree than the others. And we swap out the always strategy with the enthusiastic strategy. We get a completely different topology, a completely different structure. And we can actually see that the strongly connected component discovered, or the sink, is actually very small here. So we've seen that the concept of an attractor in a complex system can kind of correlate with the sink strongly connected component of a network. And the nice thing about this approach is that not only can it handle more strategies in this sense, but this approach can also be applied for any other discretized system, because it's essentially a state transition system. There is still kind of limitations when it comes to trying to apply this to a continuous system, but there are different ways that we can approach it, and that's something to be looked into. Again, thank you for watching. My name is Shane St. Luce, and I'm now open for questions.
Thank you very much, Sen. Are there any questions? We have some time for questions. Sen was on time. Elias, you're clapping or you have a question?
I was clapping, but I actually found, but I found the presentation very, very interesting. So I saw that you tried with up to 4 strategies. Did you try with more? I want to know a bit, what is the time complexity or the resource complexity to build these networks? Do you have to explore the whole environment, so the whole system, or after building part of the network, it already gives you some cues of which parts of the system you should explore more to have good enough knowledge of your dynamical system?
Sure. So to answer the first part of the question, yes, I did try with more strategies. Just the time it was taken to make the visualizations took a lot longer than expected. But I'm in the process of doing the same for strategy sets of 5 and 6, size 5 and 6. Mm-hmm. Additionally, can we analyze a portion of the system and try and see where that leads? I think doing so is kind of like starting from a small subspace within the possibility space, right? And then working from there. And I believe that that would be possible. It's not something that I've thoroughly tried to look into yet, but it is something that I think is a very good question that I have as well.
Okay, thank you. Very nice talk. Bye-bye.
Okay.
Thank you.
Thank you. Is there any other question? Is everything okay? Yes. Do you listen to me or I have...
Yes. Can you hear?
Okay.
Yeah.
Yeah. Okay. So, is there any other question to Shane? Just the last question from me then. Did you try to measure other measures, other quantities of these networks, saying like clustering coefficients, etc.?
Yes, I did. One particular metric that was very striking to me was harmonic centrality. I was actually able to find that, it was not presented at all here, but I was actually able to find that the harmonic centrality was a very good indicator of whether or not a node should be in the sync strongly connected component once the network was developed. In fact, I had, in some of my tests, it was 99+% accuracy. And so it's something I'm still looking into, but
okay.
it seemed very promising.
Okay, thank you. Is there any other question to Shane? Okay, thank you, Shane, for your very interesting talk, and all the people for the questions. And we pass to our last, but not the least speaker, Andreia Sofia Teixeira, if I pronounce well.
Yes.
With the title Fairness in Multiplier Ultimatum Games Through Degree-Based Role Assignments. The step is yours, Andreia.
Thank you very much. Let me know if you can see my screen.
Yes, that's fine, and we hear you.
Perfect. So today I will be presenting about the multiplayer ultimatum games in complex networks. I know that we already heard a little bit about the ultimatum games, so forgive me if I will repeat some of the concepts. So the goal of this work that is a joint collaboration with Francisco Santos, Alexandre Francisco, and Fernando Santos, is to study what is the impact of having a specific network property, in this case, the degree of an agent in a network. What is the impact of choosing the proposer with this kind of characteristics in the network? What is the impact in the fairness, in the outcome of the ultimatum game when we play it in groups? So let me check if, yes. So we know that, and this was already said in some of these presentations, that from social contracts to climate agreements, individuals have to engage sometimes in groups that must collectively reach some decisions, and these decisions can reach also varying levels of equality and fairness. So we are using the multiplayer ultimatum game, but let me go first through the two-player ultimatum game, the traditional one, in which we have a proposer that has to divide the resource with a responder. And we know that this two-player ultimatum game has shown some evidence that the process of payoff maximizing outcomes are frequently at odds with fairness. So just revisiting a bit the two-player ultimatum game. So we have a proposer and a responder. The proposer will share part of the resource with the responder. And if the proposal is accepted, then this amount that was proposed is shared with the responder, and the proposer keeps the remaining. So in practice, the way that we model this is each agent has two strategies, P and key. P is the strategy of how much I am offering. Key is the threshold, the minimum threshold that I am able to accept the proposal. So we know that in these dynamics, actually, if we reason a little bit in a backward fashion, for the responder, it's always better to have like a lowest key, so he always gets something. But of course that the proposer, knowing this, will also want to propose the minimum possible. And of course, here we have the only supreme perfecting equilibrium is when both P and key are very close, almost to nothing. So the proposer gets almost everything. And of course, this is unfair. And here I want just to reinforce that when I talk about fairness, I'm talking about the amount of the resource that I'm willing to share. So what changes when we go from the two-player game to the n-player ultimatum game in groups? So we model these dynamics now having anyway a proposer, but now I have a group of responders. And for this proposal now to be accepted, what happens is that, okay, each agent will have its own key strategy, and the proposal will only be accepted if M of these responders, if a given amount of these responders accept the proposal. So the process is, so given their own strategy, each agent will then now compare their strategy keys, so the minimum amount they are willing to accept, with this sharing of the resource. So now P has to be shared by the size of the group. So this is an example when we have a group of 4 people and I have a threshold of 50%, if 50% then accept the proposal, the resource will be shared with all the group. So our question is, how does group formation affect the emergence of fairness in a population? And moreover, what is the impact when we play this game in complex networks, when we have heterogeneity in these connections? And now we will decide who is the proposer based on the characteristics of the network. And in this presentation, we are exploring this role assignment based on the degree. Then the second question is, okay, we are in these complex networks, in this heterogeneous network, we have group formation that I will explain a bit later how we form the groups. But besides the topology of the network and the degree assignment, what is the role then of the majority threshold and also of the group size? And the framework that we use is similar to the ones that were used in previous presentations. So we are using social learning with evolutionary game theory. So in this process, we allow the strategies to spread among the network, and the most successful strategies, of course, are imitated among neighbors. So the group formation then is, each group is composed based in a central node and his neighbors. So for example, the blue node participates in the group in which he is the central node, but he also participates in the groups in which the neighbors are the central nodes. So how does it work, the selection based on the degree centrality? So we have this parameter alpha that we make it vary from -2 to 2 to model this difference in the importance of the degree assignment. And this variation on the alpha parameter makes then the degree have a higher or lower impact when selecting the proposal. For example, when we look to the toy example on the left, we can see that A will be the proposer in most of the times when the alpha is positive, so when alpha is 2. But for example, when then alpha is -2, the lower degree node, the node 2, for example, will have a higher probability of being the proposer. And of course, when alpha is equal to 0, we are doing a random assignment of this role. So our settings, we did some simulations with population size of 1,000 agents and 10,000 agents. I will present results for the 1,000 agents because the 10,000 are very similar. And for the heterogeneous networks, we used 2 different models. So one with the Barabasi and Albert growth and preferential attachment, and the other one, the duplication model by Dorogchev, Mendez, and Samukin. And we also tested different average degrees, so different group sizes, and the strategies are are first attributed in the network with a uniform distribution between 0 and 1, both for P and Q. So we start by analyzing the effects of alpha in the average proposal, so in the fairness outcome of the game. And we can see that attributing the role of proposal to higher degree nodes reduces the overall fairness level in a population. So these results are then for the both networks that I just mentioned and for average degree 4. But for average degree 8 and 16, actually the trend is the same. So when we have lower degree nodes being the proposers, the outcome is much better in terms of fairness. So we are confirming here that the low degree proposer assignment actually maximizes the strategy P, so the fairness for different group decision rules. So for both when we have 10% of agreement, 50%, and 90%. We also explored what is the average payoff depending on the degree of the agents. So on the x-axis is the degree of the agents, and then on the y-axis is the average payoff per game. And we can see on top of decreasing the average level of proposal in a population, we found that attributing the role of proposer to highly connected nodes decreased the level of fairness and equality within the population. So in these scatter plots, we are able to observe that the average payoff obtained per game for individuals with a certain degree, it varies a lot from being like the lowest degree and the higher degree. So we have a higher discrepancy in the average payoff per game when the proposers are the ones that have the highest degree centrality. We can also observe on the lower panel that making the threshold of group decision being 90%, this discrepancy is attenuated. So we can see that even though the degree centrality has a big impact in the outcome of the game, when we make the threshold of the group decision increase, so when we now make 90% of the group to agree for the proposal to be accepted, this discrepancy decreases a little bit. And we confirm this inequality, but also this attenuation of the inequality with the so-called Lorentz curves that are often used to compute the Gini coefficients. That is a typical measure of income inequality. And each curve is generating by ordering the individuals by increased value of income. And then we plot the corresponding cumulative distributions. So this means that curves that are closer to the perfect equality, so the line in 45 degree, we observed that, again, assigning the role of the proposer to high connected nodes, so when alpha is equal to 2, yields to unfair outcomes, so the orange line. And while this is very evident for a soft decision group, so for 10%, we can observe again that when we increase the threshold for group decision, these curves approximate a little bit. So there is some kind of reduction of unfairness when we have high degree proposers and a high threshold of group decision. So the main observations are that we have like levels of fairness vary when playing the multiplayer ultimatum game. This fairness can depend on role assignment, as we see with the different degree centralities, and that the effect of role assignment also depends on the group environment. And we also were able to observe then that even when we have a baseline set scenario in which high degree nodes make less fair offers, having a higher threshold group decision can attenuate this effect. So these are my colleagues, and this is all. Thank you very much. And I'm here also for questions. Thank you.
Thank you, Sofia, for your very interesting talk. Are there any questions, Sofia?
I have one question if I have some time.
Yes, of course, yes.
Thank you for the talk. It was really interesting. I particularly like this result that if a node is very connected and you give it the power to propose, then you end up with an unfair situation. Does this kind of mean that it is better not to give power to influential people, at least if influential people should be surrounded by people that have a higher threshold?
Yeah, so that is a very interesting question. Actually, in the beginning of the project and when we started to finding these results, I actually used to joke like power to the people, in the sense that when you have this more modest agents in the population, we get a better outcome. And I believe that what at least this mathematical model and the simulation show is precisely what you are saying. So even if we have very powerful people proposing whatever it is in hand, if you increase this threshold, this demanding on acceptance, maybe we get into at least midway in the fairness situation in the proposal. This is very interesting, actually. And yeah, you are right. So we would like also to have some kind of setting with real human experiments, of course, to confirm the simulations. So that would be like a next step for sure.
And do you think if the network was mutable, I mean that participants could choose to change their connection, this highly influential people that are proposers would still be connected to a lot of people, or you think that the network will change to some configurations that promote fairness? So you think that if the network could change, it will move to a more fair or a more unfair result?
Well, that is a very interesting question. And actually that will make a very nice future work because, well, even though we are working with static networks, we all know that networks in real life are not static at all. And of course, depending on the outcome of your experiences with the people that surround you, you tend to adapt your connections. So I believe that, of course, the network would not be the same, but if these effects of degree centrality, for example, if they are still observed, it's a bit difficult to say what will happen and what will really, so how this, because then we are also now going towards kind of, I don't want to say polarization, but we will have communities probably more well-defined. So yes, I believe that is totally a very interesting study to do in the future. Thank you so much.
Thank you for the presentation. I'll let other people ask questions.
Yes, are there any other colleagues that want to ask a question to the speaker? Okay. I think I would like to thank us again for a very interesting presentation, and all the speakers for their interesting presentations, and all the audience for being here and asking questions and participating in this session. I think we have finished, but there is a poster session, I think, which starts at about a quarter of an hour. So you are welcome to visit the posters there. I was glad to meet you here. Hope that in the future we meet somewhere in another way. And I wish you a nice continuation of the conference and everything to you. Thank you very much.
Thank you.
Thank you for being here.